Hello everyone, good to see you. Good to see everyone here. My name is Luke Hopkins, Developer Relations Engineer for Android XR at Google. Today we have John Bates with me from the Google Maps team, and we have Max Kim from Samsung. And we're going to be going over a lot of the performance optimizations that we've been making, and other tools and features that are available for you. For traditional apps and games, poor performance is pretty frustrating. With immersive experiences in XR, it's really been well researched that poor frame rate doesn't just annoy users, but it can also make them dizzy, nauseous, and even give them a headache. As per our guidelines, we want to hit 72 FPS, but ideally we really want to be aiming for that 90 FPS with an 11 millisecond frame budget. These aren't just arbitrary numbers, they're the difference between a comfortable user experience or one that sends users reaching for a bucket. I'm going to hand it over to Max from Samsung now to talk over the features that are available in Android XR for Unity.
Thank you, Luke. Let's look at some XR-specific features that will give power performance gains. The Unity OpenXR Android package gives access to setting frame rate resolution performance settings, foveated rendering, vertical subsampling, and application space swap. Let's go over each feature. When developing Unity apps for Android XR, the first consideration for performance and power optimization is setting appropriate frame rate and resolution. Galaxy XR supports 72 and 90 Hz frame rate options. If your app's rendering workload is not heavy, it is recommended to set it to 90 Hz. However, if the rendering workload is significant, 72 Hz, which is default, is better choice. Selecting the appropriate resolution for your app is also crucial. Galaxy XR supports 4K display resolution per eye. If your app's rendering workload is low, choosing 4K max resolution is a good option. Otherwise, it is advisable to select the default recommended resolution. While you can set the default frame rate as a resolution in the app setting, you can also utilize the performance settings feature to dynamically adjust these parameters in real time based on app and system workload. This approach ensures optimal performance and power efficiency for your Android XR application. If the application can inform the system of its current workload status, and conversely, the system can inform the applications of its current workload status, both can adjust accordingly to deliver sustainable performance without overheating. This would be highly efficient. Android XR provides the capability enabled by performance settings feature. The application can determine the appropriate CPU and GPU requirements to deliver good user experience and communicate this information to the system, ensuring it obtains the necessary system resources. For example, if the app is displaying a screen with a low rendering workload, it can provide power-saving hint to the system for GPU, reducing overall system load while maintaining app performance. Conversely, in situations requiring significant CPU and GPU resources, a boost hint can be used to allocate the necessary resources from the system. But the caveat is that it should be short. We talked about how the application can provide performance hints to the system to achieve a balance between performance and heat generation. Conversely, it can also receive performance notification from the system to ensure stable performance. By subscribing to performance notifications from the Android XR system, the app can receive notifications in the category of compositing, rendering, and thermal, with states such as normal, warning, and impaired. For example, if the application receives a warning notification in rendering category, it indicates that app is not delivering rendered frame to the system within appropriate time. In this case, the application should take measures to reduce CPU or GPU workload to return to a normal state. This bidirectional communication allows the app to dynamically adjust its behavior based on system performance, ensuring a sustainable user experience. Foveated rendering essentially mimics how human vision actually works. We only see fine detail in the specific area we are focusing on, while everything in our peripheral vision is blurry and low resolution. But our brains fill in the gaps and we do not notice. Foveated rendering does exactly this. Depending on your implementation, it can either statically render the center of your vision, the screen, in the full detail, or use your eye's focal point via eye tracking to provide highest fidelity at exactly you are looking. Pixels rendered farther from this point will be rendered at progressively low resolutions. With this feature-enabled Unity can spend less computing time in the region that are marked to be rendered in a low resolution. To do this marking there is a texture called a fragment density map that demarks the low resolution regions to be rendered. In this example, we can see regions at work here. Notice how the buildings in the background are blurred. Notice the segment of texture which is blurry. This is a great example of foveated rendering at work. First, starting by going into your OpenXR settings, enable features AR session and foveated rendering. Also make sure you have the rendering API set to SRP. Next, you will need to request for eye tracking permission if you wish to switch it to gaze mode. Otherwise, the API will fall back to static foveation. Here is a quick snippet of code showing how to set foveation level and set it to eye tracking. Vulkan is our recommended graphics API for creating immersive contents. And with that, Vulkan subsampling is foveated rendering's best friend. Foveated rendering results in lower GPU render resolution in peripheral areas. Vulkan subsampling stores those low resolution pixels in the frame buffer. This reduces GPU memory bandwidth cost and makes foveated rendering look softer. When enabling Vulkan subsampling with foveated rendering, you will free up resources to ensure you can hit those performance targets for your toughest scenes. Where targets may vary across devices, these features are ensuring you are freeing up resources on the GPU. To enable subsample layout in the Unity editor, open the OpenXR section of XR plugin management, and under all features, enable foveated rendering. Use gear icon to open foveated rendering settings. Under feature settings, enable subsampled layout. Space swap is another powerful XR optimization that helps maintain high frame rates by synthesizing every other frame. The techniques uses motion vectors and depth data from previous frame to predict where pixels should move. This means your GPU only has to render every other frame, and XR space swap fills the gaps using reprojection. This significantly reduces GPU computation power and energy consumption. It will ensure that composure runs at a smooth 72 or 90 frame rate. This is especially useful when you've got complex scenes that would normally push you over your frame budget. Space swap provides a great way to meet your frame rate objectives. However, we advocate testing space swap within your specific scenes, as its effectiveness and potential for visual artifacts can vary based on your application's use case. Enable this feature is straightforward. You can activate application space swap in your OpenXR settings, and then configure use right-handed NDC. Now, then you have enabled space swap, you also need to enable motion vectors in your shaders. Compatible shaders include lit, unlit, complex lit, simple lit, baked lit, and custom shaders, underbar XR motion vector paths, and subsample decoration. I'd like to hand over to Luke for performance profiling.
Thank you very much, Max. Now, all these optimizations sound great, but there's a critical part. You absolutely must measure their impact. Without measurements with these tools, without measurement, you're pretty much just guessing. So with tools such as performance metrics, the Unity Profiler, Foveated, and Xtrace, you can easily measure your performance. Before looking at some of these tools, let's just talk a bit about the workflow that you need to apply when looking at doing some of these performances. First, we'll establish a baseline. So before making any of these changes, you'll want to apply your optimization, measure that impact, and then iterate. This data-driven approach means you're actually improving performance rather than just guessing. It's also worth noting that some of these optimizations may either focus on the CPU or the GPU. So each technique discussed will specify where the optimization kind of takes place. Meaning ideally, you'll kind of continually profile your application, you look at optimizing your performance, and you'll keep doing this in a continual cycle. Now we know the best strategies for profiling your application. We're going to review 4 tools that are going to make it really simple for doing these things. So first, we have the performance HUD. So this, before we're hunting through any code, before we're attaching our debuggers, we can easily profile your application by going into developer tools and enabling the performance metric. Here we'll get a clear view of your timelines, your CPU, and your GPU. So it's just a great way to get some visual indicators in your application before you start debugging things and go through everything. Next, we have the Performance Metrics API. This is a real-time monitoring of your application's memory usage, CPU performance, and GPU performance. It gives you that comprehensive data from the compositor to runtime layers, so you can exactly see what's going on. Before enabling something like foveated rendering, your GPU frame time might be 13 milliseconds. After enabling foveated rendering, you'll measure again and you'll see the difference in the Performance Metrics API. Without these metrics, you're flying blind. So the Performance Metrics API tells you exactly what's happening, which makes it a great API to use. Now let's look at how to query this data so we can accurately track what's going on. Here we can get the performance metrics. We loop through all the parameters that are available to us. And then from there, we'll use a try get to get the values from the device itself. Here we have a list of supported metrics that you can query on Android XR. From querying the application to the compositor, these APIs will make sure you're getting the most out of the device. Next, we have the frame debugger. So the frame debugger is built into Unity. It's great for understanding how your scene is being rendered frame by frame. It shows you the sequence of draw calls and lets you step through them to verify your optimizations are working as expected. Want to confirm that the SRP batcher is working? You can look for the render loop new batcher entries in the frame debugger. If you want to check if the GPU resident drawer is batching properly, you can look for a hybrid batch group entities. These are visual confirmations that will help you understand whether your optimizations or settings are actually taking effect. This is a great tool that's built into Unity. For more information on Unity's frame debugger, you can check out their developer website. Next, I'd like to hand it off to John Bates, who's been doing some really interesting work and advanced profiling tools at Google Maps. And I want to talk about how developers can dig deeper with Xtrace and Foveated.
All right, thanks, Luke. So for the last few years, I've been working on graphics and performance for Maps Immersive View XR to stream photorealistic 3D map content at smooth frame rates. We've had to solve countless performance problems. We capture traces while reproducing frame drops, open them in the Foveated UI, and scroll through the data to find the problems. Xtrace is a new tool to speed up this process. It's designed to trace and answer the most common Android XR performance questions with simple commands. Let's look at what you get when you run xtrace from the command line. When the trace completes, you can see a whole lot of stats are dumped. Each row is a process that was found doing some kind of frame update, either CPU or GPU activity. The top 2 rows are typically the immersive app and the compositor. So these stats answer many questions right away. How many milliseconds of GPU time was used per frame? How many frame drops were there? Is it GPU bound or CPU bound? Compare these stats between 2 builds or app modes to answer questions like which shader is faster, which graphics mode is best, how much did an optimization help? You can also measure your own trace events if you instrument your code with atrace, Perfetto, or Unity profiler markers. Sometimes, though, you still need to dive deeper into the trace data. For that, xtrace still opens the Perfetto UI with all the gory details. Now let's look at a GPU trace example. This is one frame of GPU events. The top surface event represents a frame buffer being rendered and written to DDR memory. Under the surface event, you can see a binning event on the left, a bunch of render events, and 2 preempt events. The Adreno GPU splits up the frame buffer into smaller tiles that fit into GMEM. It's fast on-chip memory. Each render event is one of those tiles being rendered and then written out to the frame buffer. You can click on the surface event to get all kinds of details like tile counts, resolutions, and attachment info. During the binning event, the GPU figures out which tiles each triangle intersects. Triangles are binned into lists for each tile they hit. The preempt events are the XR compositor, arriving just in time to scan out the last frame to the display. So if you zoom into the space between 2 renders, you'll see the GMEM load and store events. In this case, we see 2 store color events. That's typically what you want to see for simple forward rendering. One store for the right eye and one for the left. Notice that there are no depth events. That's because depth was never written out to DDR in this case. Depth was only needed in GMEM while rendering. If you do see depth events here, and there is only one render pass, check your OpenXR settings. Make sure to enable optimize buffer discards. If you have multiple render passes, it would be expected to see some load events in here. So here's a common problem, a performance problem that you can discover in this view. In the first case, you see 3 surface events for the one frame. Those are 3 render passes being written and read from DDR, even though we expected only 1. We expected 1 because this was a simple forward rendering app. It doesn't have a shadow map or post-processing or deferred rendering that could add legitimate additional surface events. So this is costing us extra GPU time for resolving and unresolving the frame buffer to DDR multiple times. In this case, it was caused because there was a custom URP raster pass, which was missing the foveated setting. Since all other Unity passes automatically have the foveated setting, the GPU must render this as 3 surface passes. First one foveated, then not foveated, then back to foveated. By adding the foveated setting to our custom pass, all 3 passes merge, and we get a big chunk of GPU time back. Some of these cases will not show up in the Unity render graph viewer or frame debugger, so be sure to check the xtrace GPU2 results after adding any advanced render settings or custom passes. Here's some sample code that should make a custom URP pass that merges nicely with other Unity passes. Notice how the attachment and foveated rendering settings must match. Now let's look at a frame drop example. In Android XR Perfetto traces, you'll see events in the surface finger plot process that indicate when an immersive app drops a frame. Search for reprojected to jump to those events in the Perfetto UI. As you can see, I've found a frame drop indicated by this reprojected event. Now I can mark that by pressing M and look at the app threads to figure out why it was late. So the tuning workflow typically looks like this. Run xtrace, zoom in, find the cause of frame drops. If it's GPU bound, check the frame debugger for problems like too many objects or overlays. You may need to reduce resolution or simplify shaders. If it's CPU bound, find hotspots in the Unity profiler. And to see your own components and Perfetto results, add profiler markers to the expensive update calls. Now back to Luke to talk about some GPU features.
Thank you. So I think it's powerful that we have the suite of these tools so you can validate your optimizations at different levels. So we're not just talking about something that works, you kind of get concrete proof that you can see that these optimizations are taking place. So speaking of, we're going to speak about 2 GPU features that can have a huge impact on your performance, especially when working with complex scenes. So we have the GPU resident drawer, which automatically uses GPU instances to batch together similar objects. So instead of the CPU telling the GPU about each individual object, create hundreds of draw calls, Unity will intelligently know how to batch these similar objects together and send them to the GPU in batches. Picture a forest scene with 200 trees even, and they all have the same base mesh. Without GPU resident core, you've got 200 draw calls, and enabling this feature will make sure the GPU intelligently instances those trees, reducing its draw calls to about 5 to 10 draw calls. This is a massive CPU saving that you can invest in gameplay logic and physics calculations. Next. Sorry, can we go back one? Yeah. Next, we have GPU occlusion culling. So you can lower the impact of your CPU with GPU occlusion culling, which uses the GPU instead of the CPU to identify and skip rendering the hidden objects. This is particularly powerful for interior spaces. So let's say you're building a multi-room experience, rendering a lot of these hidden objects for you. Next, we have a few edge cases. So I want to bring John back up to the stage and talk about some of the edge cases experienced in Google Maps himself.
Yeah, so one surprise is that foveated rendering has its own GPU overhead. The highest level of foveation is usually an overall speed up, but other levels can sometimes be slower. Be sure to measure GPU frame times for your particular content to compare these 2 cases. Foveated rendering completely disabled in settings, and foveated rendering enabled at your desired level. Low resolution Z is an Adreno GPU feature that can skip rendering of some occluded geometry. It can be most effective in cases of heavy opaque overdraw or expensive shaders. You may need to enable front-to-back sorting to get the most value from LRZ. However, LRZ does have its own GPU overhead, so in some cases it may actually be slower overall. If you're trying to get the most out of your GPU frames, try with and without LRZ. There's no explicit way to disable it. Instead, you can draw with Z-test set to always to convince the GPU driver to turn it off for that frame. For Unity XR apps, the first thing that draws each frame is the built-in XR occlusion mesh. To disable LRZ, make a copy of the occlusion mesh shader and modify it as shown here. Now, all of these optimizations we've talked about, like foveated rendering, space warp, GPU culling, they can help you hit your frame rate targets. But what happens when you need to dynamically load content, when streaming in new geometry, new textures, and you absolutely cannot drop frames while you're doing it? Here are a few techniques that we've used in Maps XR. One of the common issues that comes up with streaming content is garbage collection hitches. These hitches become more frequent with too many temporary allocations. Look for activity on the GC finalizer thread in traces. That will often come just after a GC pause. When you see this happening too much, it's time to open up the Unity profiler, look for GC alloc events, and try to remove those allocations from your code. These cases are often easy to fix. For example, sometimes all it takes is replacing a small class type with a struct or replacing a for each loop with a for loop. Object pooling takes a little more effort to set up, but it's a good strategy if you have to create and destroy lots of objects. Another common source of frame drops is when loading textures. To create a texture 2D, we often copy data, image data, on the main thread, and then see even more work on the render thread as Vulkan resources are created. Rate limit those texture loads to minimize frame drops. And finally, by default, Android apps can use only around 3 gigs of RAM. If that's not enough for your application, you can enable large heap in the Android manifest to access more. So when you've already optimized and there are still issues during particular short sequences or interactions, there are a couple last resorts. If garbage collection is randomly causing frame drops during critical user interactions, you can just disable it for a while. But keep in mind, once you re-enable it, there might be some frame drops as it catches up with all the generated garbage. And you can also request a boosted CPU frequency with the Performance Settings API, as Mark's mentioned. Of course, if the frequency is boosted too long, it can lead to thermal throttling. And thermal throttling can be a worse experience than the default settings. So it's best to limit this to critical interactions that need to be smooth. For example, during Maps.XR user locomotions, we use CPU boost and disable garbage collection. Thanks.